So, hello everyone, my name is Johan Torsner from Ericsson, and I will talk about Internet of Things, and mainly about connectivity for Internet of Things. And for those of you that haven't heard anything about this topic before, Internet of Things is to a large extent about connecting things. As the term Internet says, it should be done sort of with Internet technology, meaning IP technology. And the reason for that is, of course, that we want all these devices to be able to talk with each other. So it's not enough that they are connected. Any device should be able to communicate with any other device. And this is what we call the Internet of Things. I will say a little bit about the general topic and then spend most of the time on the actual connectivity issues. But before going into that, I want to show one PR slide about who we are, and I'm sure you know who Ericsson is and what we do as a company, but maybe you're not so familiar with what we do here in Finland. We have around 1,000 employees in total. 650 of those are in R&D, and our main R&D site is located in Kirkkonummi, half an hour west from Helsinki, where I am located. And there we have another rather big R&D site up in Aalto, also working with radio issues. We are involved in all parts of the communication field, both when it comes to developing solutions and products for the telecom industry, and also telecom services, mainly to mobile operators. Another area which I think you may not be aware of is that we are involved in the TV and media broadcast area. So we are managing, for example, MTV's TV broadcast system here in Finland. So that was very short with what we are doing, and of course if you want to know more, there's a lot of information available on our webpage. And then Internet of Things. But before going into that, I want to talk about sort of the general success story of mobile communications, and that has so far been mobile broadband, the communication between people. And then I have two pictures here just showing how rapid the development have been in this area. You might have seen these pictures before, because I know some other people have shown them as well. This picture here is taken outside the Vatican City in 2005, when people were listening to the speech of the Pope. And it's nothing spectacular with that. And this is sort of the same angle in 2013. And you notice sort of the enormous difference here in people's behavior. They had obviously mobile phones already in 2005. Some of them have them also in this page. But the way the people are using them have changed rapidly in just a few years. Now, people are taking videos they are sharing with the friends, and it's sort of a completely different way of using these devices. And here you realize that in order for this to work, it's not enough to be able to take a video and sort of upload it to some server somewhere. You really rely on that all your friends can also receive this video and see what you're seeing. And that's why it's so important to have solutions which are interoperable, so any device can communicate with any other device. And it's the same thing when we talk about connecting small things then. So what we are saying then is that when one thing or one person connects, it's their own world that changes, but when all everything is connected, the whole world changes. And this is then part of our vision in Ericsson about the network society. And everything here, of course, means a lot of things, from sort of trivial things that you can imagine that you would connect, like an electricity meter, down to very small things like a connected toothbrush or pen or something like that. And this is a trend that we see right here. And this development has already started. I mean, you see every day in the papers that there are new products in consumer electronics, for example, coming out that are connected. Many of them today are using Wi-Fi or some other existing system. And this is a trend that is going very, very fast. And I have some statistics on how fast it's going. So right now, we estimate that there are 13.5 billion connected devices in the world. 7 of those are mobile phones, and that's dominating the mobile or wireless connectivity at the moment. In only a couple of years, until 2020, we think that this number has doubled. But the growth is not really coming from the mobile phones anymore. It's still growing, but relatively slow. So the main growth here is really coming from connecting other things. And sometimes we call that machine-to-machine communication, sometimes it's called Internet of Things, and there are other names for this phenomenon as well. So machine-type communication together with the connected consumer electronics is going to grow very, very fast in the next couple of years. And if you're interested in these kind of statistics, there is a lot of graphs like this on our homepage that you can download, and you can even design your own graphs if you like. If you want to see per area or per technology or something like that. So you just go to our external homepage and you search for Ericsson Mobility Report, and you can create this kind of graphs there. As you might expect, the fixed phones are not growing at all, so it's actually decreasing, and this is a trend that started several years ago. So we see that the speed of change is really increasing over time. It took our industry about 100 years to connect 1 billion places, and places that means that you have a fixed phone in your office or at your home and so on. So that was a relatively slow build out of the fixed telecommunication network. And when we started to connect people with mobile communication, this went much, much faster. So in only 25 years, we were able to connect 5 billion people. And when we then move into connecting things, we think that this will go even faster. So in 15 years, we think that we will have 50 billion connected devices. And they can be connected in many different ways, but most of them will be connected wirelessly. And you see here that this number, 50 billion, I put that here roughly around 2020. And then there's a mismatch between this figure that talked about 26 billion connected devices in 2020. And the reason for this is that this, first of all, this is a vision. The other one is actually a quite detailed forecast built on measurements in many networks around the world. But also that on this vision slide, we talk about anything that can communicate as being a connected device, whereas in this forecast, you need to have some intelligence to be considered a connected device. So for example, you need to be capable of two-way communication. You must be able to both transmit and receive. And you need to have a processor so you can actually process the information you receive, and based on that, change the information you transmit. So if you're a very simple temperature sensor, for example, that only transmits and not receives, then you will not be counted as a connected device in this forecast. But regardless if we're talking about 26 or 50 billion connections, there will be very many, and the change is happening very fast. Internet of Things, it's really about creating a digital representation of physical objects. And for each object on the left side, you can sort of see the corresponding digital representation on the right side. So for a bridge, for example, there could be aspects as the road temperature, the vibration, and these kind of things. And when this digital representation is available, you can base a lot of services on this information, but only if all these different type of equipment really talk the same language. So if a car, for example, is going to make use of the information from the bridge to know if it's windy there or if it's icy or something, you really need to have interoperability on all the way up to the data semantics there, so you can really correlate this information. And that is a real challenge. I mean, it's not very difficult to put sensors on a bridge and communicate that up to a cloud, and then you build an app that displays that information. That would be rather straightforward. But for all these different systems to interop in a way so that they could be devices made by different vendors, coming from different industries, and so on, that is a real challenge. Since there are so many different kind of devices that can be connected, they also have very different characteristics. And when it comes to the communication characteristics, we normally talk about machine type communication, and we sort of separate this into two groups that we call massive MTC and critical MTC. And massive MTC, that is what you could imagine when you hear the term Internet of Things. So they are rather small things that are connected. They don't generate very much data. It's maybe delay tolerant, so it doesn't really matter if the information is received immediately or not. And there could be a very large number of these devices. And since they are small and cheap, also the connectivity solution needs to be simple and cheap. And that is what we call a massive MTC. But then there's also another aspect of the MTC, which we call critical MTC. And these are more industrial applications that require very low latency and very high reliability on the communication link. And one example of this is, for example, collision avoidance for cars, where you need to communicate your location to other cars so that they can brake if you are sort of, it looks like you're going to collide in the next 100 milliseconds or so. And I will give some more examples of this, but this is just to show that the range of requirements on the communication is very, very wide, depending on exactly what kind of things we are connecting. A little bit going back in time to 2001, because connecting things is not really a new idea. I mean, it has been around for a very long time, and this is an early experiment by Ericsson together with Electrolux that was called the screen fridge. That was a prototype that was released in 2001. And the idea at that time was sort of to bring the fridge to the center of the home, so you could have a computer screen on the fridge where you could browse for recipes and maybe have a family calendar and these kind of things. And this was then connected via ESDN to the network. And this, of course, did not fly for several reasons. And we have some other examples of things that did not fly either. So it roughly at the same time, we had actually the world's first internet radio communicating over Bluetooth. And this is something you see in most homes now. But there was a prototype on that in 2001, but it didn't fly at all. And then there was something that looks like a very early version of an iPad, although a little bit bigger, which was a handheld device where you could use for browsing and reading documents and so on, connected via Bluetooth, and it has a dial-up modem. So all these things are example of things that we launched in 2001 in various level of commercial releases then. And nothing of this, I would say, did fly at that time. And then you can ask, why did it not fly then? And why do we think that these kind of things will fly now? And one reason for that was, of course, that the technology was not really mature enough. You could build these things, yes, but it was not cheap enough. It was not small enough. It was not easy enough to use. And if you managed to build something, it didn't really work well with other devices from any other vendor. So it was quite a cumbersome solution. Another reason was that people were not ready for this. So even if there were such solutions, people were really asking sort of why would we use this? People were not at all used to use, for example, all the apps that we have today in the mobile phone. So people today are much more used to this kind of technology, and the acceptance is larger. So these things together means that we think these solutions have a better chance now. some trends that are happening to enable this then is that the components are getting smaller and smaller. As you know, the processors are getting very powerful and very tiny. There are many companies that have powerful processors that have the size of a coin, or in this case, this is a golf ball you see here. So on the surface of the golf ball, you have this processor from Freescale where you can run a web server, for example, if you would like to do that. So, and this development has been very, very rapid. So it's very easy to develop small and cheap applications nowadays. Also on the sensor side, the development has been very, very quick. So nowadays you can find small and cheap and fairly accurate sensors for more or less all sort of physical properties that you can imagine. So and these kind of developments happen in other areas as well. And this then together with that people are more used to these kind of technologies means that now there is a much better chance of success. This is an example of a commercial product then, which I will classify as Internet of Things. It's a fitness wristband. The sales price of this is almost $200. And the content, if you look at the electronics there, it is around $7 then, if you combine the sensors and also there is some communication module there and so on. So some statements that these vendors are making, that for each new feature that they want to add, they think about $1 hardware plus some programming. So these are some trends that leads to that we now see this really massive amount of new type of devices being launched in the market. And they all need to be connected. And these are, I showed some early examples of attempts that didn't fly. These are some more modern examples that we have been involved in from Ericsson's side that are happening right now. So we have one collaboration with Volvo, for example, around connected car, where we connect the Volvo cars to a cloud environment, and we provide sort of infotainment services for the users in the car. You can download apps there. The car itself can communicate and request service and these kind of things. Another example is what we're doing with Maersk, which is a very large shipment logistic company. Driving around these containers that you see here, and we have connected those containers for them on their ships, over 300 ships. And this means first that you can control where the containers are, where they have been, what the temperature has been during the travel and so on. And you can also optimize things like the fuel consumption of the ships, and you know exactly when the shipment's going to arrive. And there's a lot of services that you can build on top of this when you have the connectivity in place. Connected smart meters, I mean, that is happening all over Europe. It's a EU regulation even that needs to happen, and we are then managing the smart meter networks in Finland, in Estonia, and other countries as well. And I think that was maybe one of the, well, a quite early example of sort of an industrial application of this Internet of Things. Connected media it is not strictly speaking Internet of Things, but here I mentioned in the beginning that we are operating this TV broadcast systems here in Finland, but I would maybe not classify that as Internet of Things. Okay, and to make this connectivity work in an interoperable way, there needs to be standards, because otherwise they have no chance of talking with each other. And I will just, to get a feeling for the problem here, illustrate that in 2009, these were sort of the main standardization bodies addressing Internet of Things and sort of the protocols needed to provide interoperability. If we jump forward to 2015, it looks like this, and this is not complete. It just shows that there are a lot of organizations trying to make an impact in this area. And it seems that the list is only growing all the time. And so there is sort of, in one sense, too many standards. So it needs to be some alignment in this field to make sure that the devices can really talk with each other. But I think all the major players also realize that, so there are efforts to reduce the fragmentation, to sort of concentrate on fewer protocols, fewer solutions, and make them scale up in volume. Okay, then connectivity. And before I jump into the connectivity, I just want to note that the really interesting thing around it, Internet of Things, is not really the connectivity. The connectivity only stands for a very small part of the total value. So the real value comes from all the services you can put on top when the things are connected. So it comes like data analytics and these kind of things. But the connectivity is an enabler that needs to be there, because if you can't connect your things, you cannot either develop these services. And when I talk about connectivity, I mainly mean wireless connectivity then. And there are, if you want to connect things wirelessly, there's mainly three technology choices you can choose from, sort of three main ways to connect things if you look at the radio landscape, and it's related to how you use your radio spectrum. So first of all, there are plenty of short-range technologies operating in unlicensed bands, and these are like Bluetooth, Zigbee, and similar systems. Wi-Fi is also placed there. And that could be sort of a suitable choice in some situations. If you only need to communicate between devices in a small area, that is very efficient. But you also normally need to connect to the outside world, and then you need some kind of gateway then to connect to to the internet. Another option is to use long-range technologies, but still in the unlicensed spectrum. And this has been happening a lot in this area the last couple of years by companies like Sigfox and LoRa. They have made a lot of press releases, and their paradigm is totally different. You don't have this gateway in the building, and instead it looks almost like a cellular system. So you have coverage over a whole country or a city or something like that, and then you can connect your devices into that. And finally, we have the licensed spectrum, and here I mainly refer to the technologies developed by 3GPP, like 2G, 3G, and in the end 5G. And I will talk a little bit about these three, but this is just to provide the grouping here. So short-range radio technologies then, there are basically three, there are many tracks on the market, but there are three dominating ones that have some kind of volume. And first it's the Bluetooth, especially Bluetooth Low Energy. That is sort of the new version of that technology. And they have early on been focusing only on connecting things to telephones like headsets and so on, but now they are also addressing the Internet of Things segment. So they are adding functionality to make Bluetooth suitable for that, such as support for IPv6 and similar things. And they have a very large ecosystem due to that you find Bluetooth in smartphones and laptops and so on that they can utilize when they introduce these new use cases. So if you have a device that can talk Bluetooth, then you can also use the mobile phone as a user interface to control it, which is very powerful. So if you have a thermostat, for example, on the wall, you don't need any specific user interface there except for your smartphone, and you can directly communicate with it, which is quite powerful. Wi-Fi obviously is very large already and is sometimes used for this kind of scenarios, but it has some drawbacks when it comes to energy consumption, and the range is sometimes a bit limited, and therefore IEEE has been developing a new amendment called 802.11ah, which is then focusing in particular on these Internet of Things use cases, adding sort of a low power mode, a long range mode, and support for really massive amount of stations under one access point. And that's also sort of, it doesn't exist any products for that yet, but the Wi-Fi community is fairly easy for them to add this functionality into existing implementations. So you could expect that the rollout can be very, very quick once they decide to do it. And this ecosystem aspect is very important. It's not, I mean, the technical brilliance of a solution is really secondary compared to the possibilities you have to roll out this in large volumes. So even if there will be another technically better solution available, which I'm not aware of, it's very difficult to sort of succeed in the market if you don't have these kind of ecosystems to build on to make a quick rollout. Then there is plenty of systems based on this 82.15.4 air interface. Zigbee is one example of that. There are others as well, more for specialized use in industries and so on, but they all use the same physical layer. Now recently, the development, it has not happened so much in this technology the last years, but now recently Google have launched this Thread initiative, which is an attempt to create interoperability between different products using this physical layer. So they are adding some higher layer protocols, they are adding some mesh functionality, security, and all that. So to create an ecosystem around these technologies. So this is then one way to handle the connectivity for devices, which is suitable if you have a local environment, like in a building or something like that. Then there is a relation also to cellular systems through something we call capillary networks, and that is where you have a gateway in the building that has a backhaul that is based on, for example, LTE. And that means that the devices can then communicate to internet via the cellular backhaul. And that also means that you can provide some features that you have in the cellular systems for these kind of devices, such as device management, security, and so on. And then manage them as if they were part of your cellular network. And that is something that some operators are interested in providing. Then some words about this low power wide area, and this was the middle box there, sort of long range technologies in unlicensed bands. Here companies like Sigfox and LoRa has been very aggressive on the market and sort of are claiming large benefits of their system compared to, well, they compare it with cellular solutions. And these are systems that are then really optimized for this Internet of Things, low-end Internet of Things use cases, meaning that you transmit very small amounts of data and you don't do it very frequently. So you can think of a temperature sensor that sends a measurement reading a few times per day, for example. That is the kind of applications they are targeting on. And the benefits they claim then is that this is very cheap. They are cheap devices. You can have battery lifetimes of 10 years or more. And compared to cellular systems, they are claiming that this is a solution that is available now. As you will see, I will talk about that, is that in the cellular domain, we're also addressing this segment, but those solutions then will come 1 or 2 years later. There are some difficulties, though, with operating these kind of systems in unlicensed bands, because the frequency regulations in these bands, the ISM bands as they are called, they are quite tough, because since any kind of system can operate there, you need some rules how you are allowed to use the spectrum, which means that you cannot transmit all the time. You need to have a very low duty cycle, you have to have a fairly low transmission power, etc., etc. So it's difficult to make this solution scale in the long run, when we will get these 50 billion connected devices that I talked about in the beginning. But in the early on, when there are not so many devices in the systems, then it probably works quite well. I can mention one commercial example that is using this kind of technology, and that is smart parking meters. That they have in Moscow, for example, built out a system where they have a few thousand sensors in the streets, where you can detect if a car is parked on that spot or not. And there you don't need to communicate very often, only when a car comes, and that is not so frequent, so you don't generate so much load in the network. And then they have a very interesting business model as well, because they correlate this data with if the person has paid or not. So if you are parked but not paid, they inform the authorities, and then they get part of the sort of parking fine for that. But those kind of systems exist. And then the third option then, which is the license band and the cellular systems as defined by 3GPP. So there are some benefits with these systems that I want to point out. And one thing is the global nature of these systems, because if you are selling a device, you really want it to work anywhere. So if you rely on these proprietary technologies that I mentioned, like Sigfox, then you could have connectivity in one city or in sometimes a country, but you don't really have any global coverage. But if you rely on 2G, 3G, then you basically have coverage, not everywhere, but virtually everywhere. Quality of service is one thing that is important, because even if some of these devices generate very little data, there's also some that generate a lot of data. So you can imagine surveillance cameras, for example, that transmit video. And you really want to be able to have those in the same kind of network, and that you can do with cellular systems as well. Whereas these short-range and unlicensed long-range technologies, they are really so optimized for this low-end segment that they can support that kind of applications. Security is very important, and here in the cellular systems you have a quite strong security that you can reuse. That doesn't necessarily mean that you need to have SIM cards in these devices. You can have the same security functionality without actually having physical SIM cards, and that's development we foresee will happen. I stopped there on that slide. Then I have one example then around wearables. So that's something that is very popular right now. There's coming out a lot of wearables for different segments. Here you have the generic type, like the Apple smartwatches and so on, but you also have more specialized things for fitness or for monitoring elderly that want to be staying at home, and you want to monitor if they have fallen or not get up out of bed and these kind of things. And the typical way of connecting these kind of wearables, it's very common to pair it with a smartphone. So the smartphone is actually then provides the connectivity to the outside world. So this is, you can call this a coupler network then, because you can talk Bluetooth to the smartphone, and the smartphone is then talking cellular. Or in some cases you even put out a gateway in the home of the person, so you can make sure that you have connectivity in the home. But of course, you would be much more flexible if you can have a direct cellular connection here, because then you can use it not only when you have your phone with you, but also when you forgot your phone at home, or when you are doing sports, you don't want your phone, or if there is some this service for elderly, maybe either they don't know how to use the phone, or they forgot it, and so on. So there are certain advantages of using a cellular connection here, but there are also then some concerns that you could have. So one concern could be the price level. So how much does a communication module actually cost? Is it feasible to put it in a watch? Sometimes it may not be. And the battery lifetime is also sometimes limiting, because you don't want to charge your batteries too often. So there are some at least perceived limitations from cellular systems for these kind of applications. And if you take an even more extreme example, that would be if you have a connected fire alarm, for example, that you have in your Mökki, then you want to have the battery to last for many years there, because otherwise you're in trouble once you need it. And also there, the sort of the cost of the communication module cannot be too high, because then you would basically not put it in. So the price point of the module needs to be much lower than what you have in a smartphone today, because then you can actually pay a few tens of euros for getting it. So the things that needs to be addressed, if you look at the current cellular systems like LTE or 2G, 3G, that are sort of not good enough for these low-end IoT applications I've shown on this slide. So one thing is then the cost of the devices, and if you compare the cost of a cellular module with the cost of a Bluetooth module, there's an enormous difference in price there. So to be able to be competitive, we need to bring down the communication module cost. The battery lifetime, if you have devices operating on battery, you can't run around and change the batteries for all your sensors that you have, and in some cases you cannot even reach them if you have agriculture sensors or sensors in the forest, etc. So preferably the battery lifetime should be in the same as long as the lifetime of the device. So we talk about 10 years or so battery lifetime. And the coverage is also an issue, because for mobile phones, if you have a coverage problem, you can easily move to a spot where you have better coverage. If you're in the basement, for example, and you don't have coverage there. But if you have an electricity meter that you have placed in your basement and you can't reach it, then you have a problem, and then it's quite expensive to fix that, because then you need to install some external antenna or some repeater or some special solution to reach those meters, and that is expensive. So those are things that need to be addressed. And then there are some things where cellular is already quite good, and then I mentioned the security and quality of service already before. But this is happening, and if you go 2 years back, the perception was that the cellular industry is not taking this segment really seriously, and that created a niche then for these proprietary technologies in the unlicensed band to come in and claim that we are cheap and we are here now and we have long battery lifetime and so on. And the cellular system could not really match that. But now suddenly there's a massive interest in the mobile industry to address these segments. So now there are evolution ongoing on several fronts. There is both on GSM and on LTE efforts in standardization to address these kind of requirements and use cases. So we have, and the requirements are very similar in all these tracks. So basically you can say that we target 10 years battery lifetime, significantly reduced device cost, and also significantly improved coverage. And I will talk a little bit more about what's happening on the LTE side, but it's just good for you to be aware of that there are things happening on the other 3GPP technologies as well. And in the end, then you can ask why do we need these 3 different solutions then for the same problem? And it depends quite a lot on the mobile operator and what kind of situation he has. If the operator has a GSM network already and want to keep that, he has the frequency band, he has paid for that, he wants to keep his GSM network, it's very attractive to just use a software upgrade, and suddenly he can support these Internet of Things devices in the same network. So that's very attractive for those operators. If the operator doesn't have a GSM network, or he for some reason want to shut it down and instead use, for example, LTE technology, then it's a more future-proof solution to build on LTE. Because if you roll out something now, you may have to live with it for 10, 15 years and so on. And then many operators are seeing that, well, installing something based on GSM may not be a good idea, let's do it on LTE instead. And then this work is happening in LTE also. And then I wanted to summarize a little bit what is happening there. So it has been a standardization effort completed on the battery lifetime. So now there is a solution in place that is called the power save mode, where we can reach this 10 years battery lifetime for some applications. And the battery lifetime, if you take the battery lifetime for a smartphone, I mean, you have a lot of things here that draws a lot of current. You have a big screen, you have a camera, you have a powerful processor and so on, things that you don't really need if it's an Internet of Things device. But if you would try to build an optimized device for these kind of applications where you send data rather infrequently, a small amount of data, the really dominating factor for the energy consumption is it's not the energy you spend on actually transmitting data, it's the energy you spend on checking if there is some message for you in the downlink. Because for a phone you need to be reachable also for incoming calls, and you need to listen like every 2 seconds or so. Was there something for me? Was it something for me? And during a day, then you need to turn your receiver on quite many times just to conclude that no, there was nothing for you. So, and by changing this mechanism into a way where we actually don't page the devices at all, then we could sort of reach and exceed these 10 years battery lifetime. There are some studies showing that you can, 15, 19 years, depending on the assumptions you make on the traffic characteristics and the batteries and so on. So these are optimistic figures, but still it shows the potential. And how this works is basically that if you don't have anything to transmit, you are basically sleeping, or you're shutting off as much as possible, and only when you have something to transmit, you wake up, transmit it. And at that point in time, you also have the possibility to reach the device in downlink if you have some software upgrade or some command to send and so on. But there is no constant checking of these paging messages. Coverage extensions, that is ongoing work in 3GPP. The target is to reach 15 dB improvement compared to what we have in LTE today, and that would make it possible to reach devices deep inside buildings, in basements and so on. If you have a well-planned network, there are actually quite few devices where you need this extension, so it doesn't have to be very efficient, and this solution is quite simple. It's just based on repeating transmissions. So you instead of sending one time, you transmit 10 or 50 or maybe even 100 times the same message to one device, and then you can reach those devices that have very difficult situations. And since those devices are quite few, the overall capacity in the network is still sort of okay. On the cost, there's also some ongoing work to reduce the device costs for LTE. And there's no rocket science here. It's just so that if you want to build a very simple and cheap LTE device, it turns out that you're not allowed to, because the specification sort of sets minimum requirements that are quite tough. You need to support quite high peak rate, you need to support a wide bandwidth, you need to support double receiver change, etc., etc. Things that you don't really need if you are an Internet of Things device. So basically, by removing this functionality or allowing manufacturers to implement these very cheap devices, we could reduce the complexity by 75–80% compared to the modules you see in smartphones today. So that is a little bit what's happening on LTE. Then I also wanted to say a few words about 5G and the relation of Internet of Things to 5G. And 5G, one way of seeing it is that it is sort of a continuation of the earlier mobile generations that we had, and sort of the 1G then was only for simple telephony, and in 2G there was more advanced telephony for all based on digital communications, and the 3G and 4G really focused on providing mobile broadband, where we had sort of the foundation in 3G. It worked. It actually works quite well nowadays if you have HSPA. But in 4G we polished that to provide a quite powerful tool for mobile broadband in LTE. And the 5G then, we don't want to see that as just providing more of the same. So now I need to check what slide I had there. Yes, okay. So obviously the expectation of 5G is that it needs to be very good at supporting what 4G supports. So it needs to provide very good performance for mobile broadband. Then we talk about sort of traditional parameters like peak rate, capacity, and so on. So that will be covered for sure. And also media delivery will be very important, because media and video that is the majority of the data volumes in the networks already today, and it's expected to grow. So that will be there. But then connected to Internet of Things, we foresee that 5G should enable a lot of new use cases that are not really addressed by the earlier systems. And here we talk about this massive MTC, as you saw, but also this the right. If you remember this figure I showed on the massive MTC and the critical MTC, so the right hand of that picture, where we have applications that require very reliable low latency communication that you find in industries, that we also see in the scope of 5G. So low latency and high reliability sort of are key requirements for designing this 5G. And then there are other use cases that like this virtual reality things, and obviously use cases that we don't even know about today. And let me go there. So one concrete example of this then is this remote control of heavy machinery that we have made a prototype about, that you see here on the picture. We showed it in Barcelona earlier this year. So you could sit in Barcelona in this in this control station there with some goggles on, and then this wheel loader from Volvo was driving in Sweden, and you could sort of remote control this thing then from Barcelona, and you could feel how it works to operate that machine. And that is one use case where the industry is quite interested to see solutions. One example is in the mining industry, for example, where there are great benefits to be able to remotely operate equipment down in a mine. You don't want to have people there if you can avoid it. but also in some cases also in the construction industry and in other fields as well. And this puts some requirements then on the communication link, because if you are too slow, if your latency is too high, then then you don't get sort of the good enough feeling when you're controlling this. And especially if you have some haptic feedback here, where you can sort of really feel that this shovel is hitting the ground. If the delay then is too large, then you would feel that, and you don't get the same accuracy in the control. So that's one example. And there are many industrial use cases that fall in this category, where you really you need this low latency communication to support them. Maybe the most talked about use cases in the automotive industry, communication between cars. Here there are very many use cases. I mentioned this collision avoidance. There is also the sort of platooning, where cars are following each other. You can imagine having a remote driven car as well as a service, etc., etc. So they have the automotive industry has sort of a long list of use cases that puts quite tough requirements on the communication. Also in factories, you find very tough requirements. Sometimes the latency needs to be below 1 millisecond there if you want to wirelessly connect different equipment. And today there is basically not any suitable wireless technology for that. So now today they use cables. But if it would be wireless, then it would be much more flexible, so you can move around. The modern robots are sometimes so small that you can basically place it on the desk, and you can move it to a new place when you need to, and so on. And these kind of use cases you can enable then. And then we have this whole tactile internet area, which was coined by some professors, mainly in Germany, I think, which relates to where you sort of interact with physical objects and you can really touch them and feel them, and it feels like you hold them in the hand and so on. And here then the claim is that you need to have very low latency in order to have an accurate feeling for these things. So these are then some examples in this area. And then I think we'll go to the summary. So we see that the Internet of Things is happening. It has already started, and the sort of trend is quite fast. This is happening very fast. And in the papers you sort of see every day new kind of devices that will fall in this category. Connectivity is a key enabler. The main value is not there. It is in the services side, but you need the connectivity. And cellular technologies are quite well equipped to handle this communication. Not everything will be using cellular for sure. There will be a niche for other approaches as well, but we think that quite a large part will be handled over cellular. And also in 5G we see that this Internet of Things is one of the major new things compared to what we see in 4G, for example. So that was all I had to say, and I think that many of you are probably not really working with the connectivity and sort of the wireless aspects here, but there are enormous challenges to solve when you look higher up in the protocol stack, and sort of on the analytics, data semantics, and interoperability there. And if we cannot solve those challenges, I think that will slow down the progress quite significantly. Okay, I think I stop there.